makes ongoing experiments on the therapeutic potential of mitochondrial transplantation using astrocytic extracellular vesicles containing mitochondria in a traumatic brain injury model. So I would like to acknowledge the lab, Sylvan's lab, as well as Brad's lab for doing this experiment and also the funding agency, K-Shirt and IH. So Pat already showed the importance of mitochondria in the traumatic brain injury, and also he showed that how the neurons of the mitochondria get affected by injury. And here I am showing the micrograph how this mitochondrial dynamics changes by just traumatic brain injury, and also it changes the function as well. So which we show by isolating the different fractions of the brain mitochondria using the magnetic field. These are neuron-specific neuronal mitochondria expressing the GOP in the outer mitochondrial membrane. You can collect all the fractions and do. Mainly the affected fraction is the synaptic mitochondria due to executive short toxicity. We believe, and also not the soma mitochondria, astrocytic mitochondria. So whenever the neuronal mitochondria get affected, there are papers showing that astrocytes are capable of giving healthy respiratory competent mitochondria to neurons. And we also showed that in a in vivo condition in capillary, and also published in the stroke model. And our question is whether the astrocytes donate mitochondria to neurons during the traumatic brain injury. That's our first question. For that, we made a model, blended mice model, expressing specifically in astrocyte. So this mice model we characterized in the lab, and it expressed mainly in the astrocyte and not in other cells. And we showed initially they are capable of delivering mitochondria to the neurons. And also, as you see, this is a 2D diagram. You can misinterpret because the neurons and astrocytes, they are very closely wrapped around. And you may misinterpret these are actually whether they are coming from astrocytes or neurons. Then I come up with the model to isolate only the mitochondria which is in the neurons to make use of the IMAX. I made a 3D reconstruction, and you can see the images actually here. And the mitochondria actually is in the cross section of the nuclear soma, which is very similar to astrocyte what we are seeing here, which is not stained with the neuron and the muscle. And you can also see the mitochondria inside the soma neuron. So the next question, this is a very complex system in vivo, so we made a very simple system by culturing, co-culturing astrocyte as well as the neuron, which is again the astrocyte specific model. So using the 4-isotype domains, we can treat the culture and make only the astrocyte express. And you can see the neurons actually they're getting the mitochondria from the astrocyte. And you can see the another neuron doesn't have any astrocytic mitochondria. And also we stain to show the endogenous mitochondria by Thomson. And there is 4 localization of mitochondria. So the astrocyte they are giving mitochondria to neuron. What is happening to the astrocyte at a transcription level? So there are several genes associated with mitochondrial biogenesis, fusion, fission, exchanging crystals in the astrocytic mitochondria, and also they are dynamically exchanging. You can see the astrocyte they are getting walled up, slender, long mitochondria. They are becoming walled up, and these astrocytes are capable of making packaged mitochondria and giving into the neurons. That is what happening in real life. We want to test that. So for that, we generated another mouse model, which actually makes the GFP in the outer mitochondria membrane instead of the dendritic mice. The dendritic is actually expressing the inner mitochondria membrane. You cannot fraction them using any magnetic field. So this one capable of fractioning because it is happening. It is expressing the outer mitochondria. And we isolated the mitochondria, and we could be able to do the CDORs using this isolated mitochondria, and also the quality we checked by using TMRD. They are capable of their intact mitochondria, and also they lose the membrane potential by adding FCCP into that. And we are not isolating any non-specific wild-type mitochondria using this mouse model. And these are the sections from the brain. You can see see there are astrocyte specific mitochondrial expression from this mice, and also you can see in between there are some spaces where there is no astrocyte, you still see the mitochondria. So the mitochondria, they are coming from astrocyte in all different directions and going into probably different cells, but we are mainly interested in neurons. And interestingly, these mitochondria is not affected by the traumatic brain injury. It is like a neuron mitochondria, and we believe that these astrocytes are capable of giving respiratory competent mitochondria to neurons. And now we are in the process of coming up with a methodology to count the number of percentage of mitochondria transferred into the neuron. You can see you can do the NIS element from Nikon. You can do the 3D construction of the images, and you can count the number of mitochondria specifically in the region of neuron. You can see the number of mitochondria using the software. This is particularly kind of software. You can say the number of neurons and number of mitochondria, particularly in the astrocyte. You can do the region of interest and count the number of mitochondria. It gives the number of neurons as well as the average number of mitochondria inside the neuron. And so we believe the astrocyte donate mitochondria to the neurons. We tried a couple of times using the isolated mitochondria. It wasn't getting into the brain. So we believe probably they are making vesicles and transferring into the neurons. So we did the primary astrocyte culture, and we collected the astrocyte containing the mitochondria, and we transplanted those in the primary neurons. And primary neurons were taken up, and we could be able to see the 3D confocal imaging. And also we experimentally made an exotoxicity by treating the neurons with the NMDA. And we then, after treating with NMDA, we transplanted the astrocytic mitochondrial vesicles. And we could be able to rescue the function of the neurons by sequence, which you can see. So this is my summary. So the astrocyte is capable of donating mitochondria even for some reason. Probably the particular neuron is under stress condition, or physiologically they need some mitochondria. They are talking to each other from astrocytes. They are giving mitochondria to neurons, even under live condition. And also they are respiratory competent, and we could be able to rescue this NMDA-mediated exotoxicity by providing the vesicle containing mitochondria. So our future direction is to make the astrocyte containing mitochondria for treating the TBI model by using this vesicle, and also how to increase the number of vesicles in the astrocyte in the functional model. And also we have evidence we can be able to cryopreserve these vesicles, and after a few weeks we can still be able to use this cryopreserved vesicles and deliver them to cells, and still they are functional. They are moving along with endogenous mitochondria in the in vitro system. So this I would like to take.
Any questions from the audience?